we are going to look at how to use Arduino Uno in order to control a micro servo using a potentiometer as well as using a automatic operation. So, and during this process you are going to learn about how to visualize the results using serial monitor and serial plotter and a few other concepts. So first log in into your TinkerCAD account and then go to circuits and click on create new circuit. Next, let us bring in the Arduino Uno board, breadboard and a micro servo into the workspace. Now the micro servo that we will be working with, the deal with this is that it has an arm which can rotate by 180 degree as we supply it with a pulse width modulated signal. Now to better understand about this micro servo, let us go to the data sheet for the servo motor. The model number that I'll be working with in the physical circuit is SG90. This is what is also modeled in TinkerCAD. Now if you look at this particular micro servo, you can see three wires coming out of this: orange, red and brown. And as you can see, you have these arms which can be screwed onto the micro servo. Now this is a really lightweight component, so you can look at the dimensions of this particular component. It has a height of about 3 centimeters, a width of about 1 centimeter, and it weighs about 15 grams. So as you can see, it's a very lightweight servo. But that said, it can generate a peak torque of 2.5 kg centimeters, which is quite a bit of torque. Now coming to the three pins that we have for the micro servo. So you have a pin corresponding to the brown cable, red cable and the orange cable. So for the pin connected to the brown wire, we will have to give the ground signal. The pin connected to the red, we'll have to give VCC, which is essentially 5 volts for this particular circuit. And for the pin connected to the orange cable, we'll have to supply a pulse width modulated signal. So in short, PWM. If you look at the pulse width modulated signal that we will be working with, you are going to provide a signal like this. So as you can see, the signal is going to have a time period of 20 milliseconds, or we'll be working with a 50 hertz signal. Now it is going to be off for most period of time, and it is going to have a pulse on time of around 1 to 2 milliseconds. And depending on the amount of pulse on time or the value of the pulse on time, the servo motor arm will rotate accordingly. So when the value of pulse on time is at the lowest is going to be somewhere around 0.1 to 0.2 milliseconds of pulse on time. So for that it will be at 0 degree position, and then for the maximum pulse on time it is going to rotate by 180 degrees. Now the servo motors are used in quite a few applications. So I am going to show you a few examples over here. So here is a project which can be executed using the Arduino board, a servo motor and a ultrasonic sensor. So we'll be covering both of these sensors in today's class. So the servo motor, as you can see, it has an arm, and you can rotate this arm by whatever angle you desire using your electronic circuit. Now in this particular project, the ultrasonic sensor is being used to detect the distance of the sensor from the person who is going to approach towards this dustbin, As he comes close to the dustbin, the ultrasonic sensor through Arduino detects that there is a person over here, and then the servo motor is used in order to push this particular lever down and thereby open the dustbin. Thereby, without anybody touching the dustbin, as soon as somebody comes close to this dustbin, the lid will open and then the person can throw the trash into that. Next, here is another interesting application involving the servo motors. So, once again, you can use the servo motor in order to change the orientation or the angle of the solar panel. So, you can use it in solar tracker applications. And another interesting application where you can use the servo motors is in robotic systems. So in robotic systems, you normally make use of linkage mechanisms, and the angle between two links, when you are using a pin joint, the angle between two links can be controlled using the servo motor. So depending on the degrees of freedom in your system, you will have to use that many number of servo motors. Now the servo motor that we will be using in this particular application, which is SG90. SG90. This servo motor can be controlled directly by Arduino. You don't really require any other special motor driver in order to control this. So, alright. So first let us look at manual control of this servo motor. So for manual control, we are going to make use of a potentiometer. So I'll bring the potentiometer into the circuit. Now the potentiometer has okay, so for terminal 1 and terminal 2 need to be connected to the voltage and the ground. Now before I start laying down the circuit, what I'm going to do is I'm going to connect a red wire from the 5 volts of Arduino to the positive pins on the breadboard. Okay, so I'll connect the red wire. So now what is happening is all pins on this row are going to be at 5 volts. Next, I'm going to use a black wire in order to connect the ground of Arduino to the ground of the breadboard. Okay, alright. Next, what I'm going to do is I'm going to connect the ground to terminal 1, and then I'll use a red wire in order to connect the 5 volts to terminal 2. Okay, so this is going to be black. Alright. Next, the output from the potentiometer, so we are giving it a 5 volts input, and as we rotate this dial, the potentiometer is going to give an output varying from 0 to 5 volts. So at this position it will be 0, and as I rotate the dial to the other extreme, the output is going to be 5 volts. So I'm going to use this turquoise color in order to connect the output of the potentiometer. So I'll connect the output of the potentiometer to analog pin A0. So this is a input pin. It's an analog input pin. So analog input you can vary from 0 to 5 volt. Okay. Now coming to this servo, so you can hover your cursor around these pins and you can read that the leftmost pin is the ground pin, the middle one is power, and the rightmost is the signal. So let us start with the easy ones. So first I'll connect the power pin to the power line, and then I'll connect the ground pin to the ground of the Arduino. Then what I'm going to do is I'm going to connect the signal I'll take in yellow. So signal I'm going to connect to pin number 9. Now pin number 9 in Arduino is a pulse width modulated pin. So for the digital pulse width modulated pin, you have this wavy symbol next to the pin. So pin number 9 is a pulse width modulated pin. Now in order to visualize what input we are giving to this servo, what we will be doing is we will be bringing an oscilloscope into the workspace. So I'm going to bring an oscilloscope, and the oscilloscope, so the negative of the oscilloscope is going to be connected to the ground, and the positive of the oscilloscope, I'm going to connect it to the positive of the oscilloscope, I'm going to connect it to the signal. Okay, so now we can see what's going on over here. And then now from the data sheet of the servo, you can see that the pulse width modulated signal is going to have a time period of 20 milliseconds. I would like to see 2 pulses on my oscilloscope. So what I'm going to do is I'm going to use a division of 4 milliseconds. Okay. So if I use a division of 4 milliseconds, then what happens is, so each of these the box width over here will be 4. So I'm going to have 4 into 5, 20 plus 20. So 40 milliseconds, I'll be able to see the signal. So I can see 2 pulses over here. Now, in order to see what is the input we are giving to this analog pin A0, let us bring in a multimeter into the workspace. So the multimeter, what I am going to do is I am going to once again use the same color. So the output from the potentiometer, I am going to connect it to the positive terminal of the multimeter, and I am going to connect the negative terminal of the multimeter to the ground. Okay, so negative terminal I am going to connect to the ground. So let's change the color. Alright, so now as I change the input, I should be able to do this. Alright, so the circuit is done. Now we need to enter the logic. Go to blocks plus text so that you can see blocks as well as the text which is being created. Go to variables. In here we will have to create 2 variables. One for reading the analog signal at pin A0, and second for providing a pulse width modulated signal at digital pin 9. So go to create variable. First I'll call it as sensor input, and the second variable I'll call it as output value. So first what I'm going to do is drag in the variables, I'll drag in this particular block which says set output value to. Now what I want to do is I want to set the output value to the analog pin A0. Okay. Now once I have this, whatever is the voltage, the output this has to be sensor input. Whatever is the sensor input that I am receiving, I want to map it to 0 to 180 degrees range, because the servo which we are using, it can rotate within a range of 0 to 180 degrees. So for that, again go to variables, say set output value to. So in math, use the map function. So what I want to do is I want to set the output value. I want to map the sensor input to 0 to 180 degree. So whatever is the sensor input, it will be mapped to this particular range. So for instance, if the sensor input is 2.5, so if analog pin A0 receives 2.5 volts, then the servo will be made to rotate by 90 degrees. If it receives 5 volts, it will be made to rotate by 180 degrees. If it receives 0 volts, it will be made to stay at the 0 degree position. Now once you have the output value, Now what you want to do is you want to rotate the servo pin. So I'll go to rotate servo on pin number. So this is on pin number 9, and to by what value do you want to rotate it? You want to rotate it by this value of output value. Okay, now when you are using the servo, what it is doing is, so it is including servo.h library, and then in order to give the input to this digital pin 9, so it is using this particular function servo dot write of output value. And after this, let us so today I'm going to show you how to use the serial monitor and serial plotter in order to understand what's happening in the code. So for that, you can go to output, because well, it's an output. So you can say print to serial monitor. Now what do you want to print? Let us first print this sensor input and then this output value. Okay, so I'll go to variables, and then I want to first print sensor input, and then after I print, it is asking me whether you want to go to the new line or stay on the same line. So I'll say without new line, and then again I'll go to output, print to serial monitor, I'll put a comma, give a space. Once again, I don't want to go to new line, and then one last time I'll use this serial monitor command, and here I want to print the output value, and this time I want to go to the new line. Okay, I want to go to the new line. Now over here, whatever logic is being executed, it will be executed in the loop. Okay, so that as you rotate the potentiometer, automatically the potentiometer value will be read by the pin A0, and accordingly the servo will be rotated. Now after this logic is executed, it is assuming a default delay of 10 milliseconds. Okay, so whenever this delay function is being used, the input to the delay function is in milliseconds. So this is 10 milliseconds. Okay, alright, so now let us see how this code gets executed and what exactly is happening within the circuit. Now in order to see the output from this code, click on serial monitor. So you see two things. So one is this place where text is displayed, and if you click on this plot, it will also display the plot. So let me bring this a little to this side, and then let me make this a bit smaller so that we can see both the circuit as well as this text at the same time. Alright, so let's start the simulation. Okay, so the simulation has started. It will be better if you can see the multimeter also. Okay, first let us see what's happening in the circuit simulation, and then we'll go to the output of the code. So right now the simulation is running. So the potentiometer initially is at 0 volts, and at 0 volts this arm, the longer arm, is vertical, and you can look at the input which is being given to the servo. You can see that it's a pulsed signal. So if I go in a little bit, you can see that the x-axis range is 40 millisecond, and each of these blocks is 4 milliseconds wide. So initially the pulse on time is much less than 1 millisecond, and then as I increase the voltage which is given to pin A0, the longer arm of the servo is rotating in the anticlockwise direction, and the input to this servo is actually this pulsed signal, and the pulse width is increasing with the applied voltage. So you can see that as I increase my applied voltage, so we are now at the maximum of 5 volts. So, and as I went from 0 to 5 volt, the servo arm rotated by 180 degrees. So you can take a keep a close look on the servo arm and on the voltage. So this is at 0 volts. So you can see that the arm is rotating in the counterclockwise direction by 180 degrees. And at 5 volts, the pulse on time is highest. It is close to about 3 milliseconds. So it looks like the pulse on time is varying between something like about 0.25 to about 3 milliseconds. Okay. Now, okay, this is what is happening in the circuit. Now let us see what is happening in the code which is executing this particular circuit. So I'll go to code. Now let me move this a little so that we can see the potentiometer, multimeter, and this output. Now the first interesting point to note is that when the voltage which is given to the analog pin A0 is 2.5 volts, the sensor input is actually coming out as 511, and the output value is 89 degree. And for these two variables in the serial plotter, two plots are being created. The blue plot is for the sensor input, and the orange plot is for the output value. Okay. Now, so what is happening? So what is this 511? Now, in order to understand what is this 511, we need to understand that even though what we are giving to pin A0 is an analog input value, before the microcontroller comes into play, this analog signal must be digitized and the binary code will be given to the microcontroller. Now, so what is this discretization? So in order to understand this, let us look at conversion of a analog signal to the binary code when we are using 3 bits binary code. So in 3-bit binary code, the different levels of the analog signal are represented using this particular notation: 0, 0, 0, 0, 0, 1, so on up till 1, 1, 1. So each of the bits can take values of 0 or 1. So what these three numbers correspond to are the coefficients of 2 to the power 0, 2 to the power 1, and 2 to the power 2. So for 0, 0, 0, it will be 0 into 2 power 0 plus 0 into 2 power 1 plus 0 into 2 power 2. For 0, 0, 1, it will be 1 into 2 power 0 plus 0 into 2 power 1 plus 0 into 2 power 2, and so on. And for the last one, 1, 1, 1, it will be 2 power 0 plus 2 power 1 plus 2 power 2. So that will be 7. So whatever is the total range of the signal, so in this case it is 2 volts, it is being divided into, it is being represented at 8 levels starting from 0 to 2 volts. So for 0, 0, 0, the digitized value is 0 volts. For 0, 0, 1, the digitized value is 2 divided by 7. Next one is 2 into 2 divided by 7. And for the last one, it is 2 into 7 divided by 7. Thus, whenever you are using a ADC, the analog signal can only be represented at quantized levels. So for instance, if you give a input of 1 volt in this particular case, when you are using a 3-bit representation, you can represent the signal either at 6 by 7 volts or at 8 by 7 volts. Thereby you will end up creating a discretization error of about 0.14 volts. In the case of Arduino, about 5 volts is being represented at 1024 levels. 1024 is essentially 2 to the power 10 because you are using a 10-bit ADC in the case of Arduino Uno. So whatever is that sensor input value you are seeing from 0 to 1023, in order to get the actual voltage which is being given at A0, you have to multiply the sensor input with 5 volts and divide it with 1023. So you can go here as you turn this. So you can see that at 0 volts sensor input has a value 0, and at 5 volts the sensor input will give you a value of 1023, which is 2 to the power 10 minus 1. Now for any intermediary value like 1.4 volts, so if I go to 1.4 volts, then the sensor input, so after going through ADC, what you get for pin A0 will be the value of the analog signal divided by the maximum value, so which in this case is 5 volts, so it is 1.4 divided by 5 multiplied by the range of values, which in this case is 1023, and we need to round off this particular number, so that will be equal to the sensor value. So if I do this in this case, I'll get 286, which is what is being printed over here. And then after that, the output value is simply the sensor value divided by the maximum value it can have, which in this case is 1023, multiplied by the output range and rounding of this number. So in this case, this turns out to be 50 degrees. Okay, so this is what is happening. So this is a very important point to remember, that what you get when you read an analog pin is not the actual voltage, but rather it is this it is the digitized level, okay, which ranges from 0 to 2 to the power of how many ever bits ADC you are using minus 1. In this case, it is 2 to the power of 10 minus 1. Now, as I rotate this potentiometer, you can see how the output range is changing in the graph. Okay, you can see this particular graph. So manually, whenever you are setting the value, you are not really going to have smooth transition. So next I'll show you how to create a small code so that you can rotate the servo motor in a pre-programmed manner, in a smooth manner. So if at all we have a requirement where the servo needs to rotate within a certain angular band in a periodic fashion, then we need to automate the process for that. So let us see how we can do that. Now what I'm going to do is I'm going to introduce a switch using which we will be able to switch from the manual to the automatic version. So I'll be using a push button. Now in order to activate the code, what I'm going to do is I'll use a LED in series with a resistor. So the resistor is a 1 kilo ohm resistor. It will become clear in a while as to why we are doing this. Let me bring in another multimeter. Now what I'm going to do is connect the anode of the LED to the positive terminal. Let me choose this as a red colored wire. Now the resistor I'm going to connect it to the push button. So this I'm going to put it in black. When the push button is pressed, then when the push button is pressed, the LED is supposed to glow. So now when you're working with the push button, one thing to remember is that the two sides are interconnected to one another. So what you need to do is connect the wires in the diagonal fashion. So the from here I'll be connecting it to the earth. So now, so if I run this particular simulation, you will see that when the push button is not pressed, the LED does not glow, and when it is pressed, the LED glows. Next, what we will do is we will look at the voltage at this point with respect to the ground. So I'll connect the terminal 1 of the resistor to the positive terminal of the multimeter, and the negative I'll be connecting it to the ground. Please note that I am connecting the ground on one side of the breadboard to the ground on the other side, and on the other side. So alright, so let me just rearrange these wires a little bit. This I'm going to use a blue colored wire. Now let us run the simulation once again and see what exactly happens. So when the push button is off, then the voltage at this particular point is 3.66 volts, and when the push button is pressed, the voltage goes to 0. Now what I am going to do is I am going to connect this terminal. I am going to connect this terminal 1. Sorry, stop the simulation. I'm going to connect the terminal 1. I don't need the multimeter now. So I'm going to connect the terminal 1 to the digital pin 4. Okay. So what happens is that when the push button is off, then the digital pin 4 will be high, because the voltage is higher than the mean value, and when the push button is pressed, then the digital pin 4 will read the low value. So based on what the digital pin is reading, high or low, when it is high, then we will activate the automatic rotation, and when it is when it is high, we will be activating the manual rotation, and when it is low, we will be activating the automatic rotation. Now let us see how we can write a code for this. So let us go to code. Now we are going to use a few other functions. So first go to control. Now in the control, we will use a if then and else statement. So I'll put a if then and else statement over here. Now so if over here, go to math and let us use this less than equal option. So let me put this here. Now what I want to compare is I want to compare the output, I want to compare the read digital pin number 4. I want to check whether this is equal to high or low. So when this is high, that is when the push button is not pressed, I want to use the manual operation. So if it is high, so for high, what I have to do is I have to go to the math, and then I'll use this particular block over here. So when the digital pin 4 is equal to high, then we'll implement the code which we have already written. And when it is low, that is when you go into the else loop, then what we are going to do is we are going to do the following. So I'm going to repeat 180 times. So I'm going to go from 0 to 180 degree rotation and then 180 to 0. So what do I do? Repeat 180 times. So what do I repeat? So what I do is I go to variables and then I say set output value to. So I'm going to pick this particular thing where I increase the output value by I increase the output value by 1 each time. Okay, and then I set. So I'm then going to rotate the servo pin number 9 to this output value, whatever is the incremented output value, and then I'm going to wait for 10 milliseconds. Okay, so what happens once I come into the else loop? So initially I'll have to initialize it. So I'll say set output value to, just one second, I'll bring this out. So set output value initially to 0, and then what I do, I'll repeat the following thing. So I'll say set output value to output value plus 1. Okay, and then I'm going to rotate servo on pin 9 to the output value, and I'm going to wait for 10 milliseconds. Okay, so this way, so it will start from position 0, keep incrementing the value by 1 degree until the arm rotates by 180 degrees. Now once that is over, I'm going to repeat 180 times. So now I'm going to go back. So for that I say set output value to output value minus 1 this time. Output value minus 1, and then rotate servo which is connected on pin number 9 to the output value, and then wait for 10 milliseconds. Wait for 10 milliseconds. Okay, alright, so this should work. Let's see what happens. Let me start the simulation. So now you can see that currently, based on whatever value is there prescribed by the potentiometer, the dial is rotating to that particular level. So if I change this, it will go to the position as prescribed by the potentiometer. Now if I press this push button instead, so then what happens is, then it is rotating by 180 degrees and it's going to do back and forth. Okay, so this way you can switch between manual and automatic modes. So what I'm going to do next is I'm going to copy this code and I'm going to go to the Arduino IDE, open a new file, remove what is there, paste whatever I have copied, and save it as servo manual come automatic. Alright, so now I have my file ready. So next I'll have to build the circuit as we have created in the circuit layout, and then I have to upload this particular file onto Arduino. Now before I move ahead, let me first check whether the code compiles correctly or not. So you can see the compilation is done and the code has compiled properly. Next, let me build the circuit and then we can upload this code onto Arduino Uno and see whether or not the whatever is the output matches with whatever we are seeing in TinkerCAD or not. So whatever is the circuit we have created in TinkerCAD, I have replicated it on the breadboard over here. So this is Arduino Uno and I have connected the pins appropriately through the breadboard to the servo motor. So this blue colored part is the servo motor and the arm of the servo motor on one side I have painted it in red and another with blue so that you can clearly see which way it is rotating and by how much. This is the potentiometer. Once again I have attached this orange colored piece onto the dial so that you can see which way the potentiometer is rotating and by how much. The output of the digital pin 9 is connected to the oscilloscope for you to see. Now in the oscilloscope, each of these bands is 5 milliseconds horizontally and vertically it is 2 volts. So the signal is supposed to come to somewhere over here at 5 volts. So let us upload the code onto Arduino and see whether or not things go as per the simulation result in TinkerCAD. I have now uploaded the code. So when I do not press the push button, so as I rotate the potentiometer, you can see that the pulse width over here is changing. So you can clearly see the change in the pulse width as I rotate the potentiometer. And you can also see that as I rotate this, the servo is rotating. But probably because I am touching the leads over here once a while, the voltage is changing and because of that you see a jerky motion in the servo. But otherwise it works on expected lines. Particularly you can see that as I rotate this to and fro, the servo arm is rotating to and fro. And you can also see that if I rotate this, okay, maybe I'll hold it over here. So if I rotate this by a complete 180 degree, the arm also rotates by 180 degrees. So you can see that it is horizontal and red is on the left. Now if I rotate this fully by 180 degree, the arm has rotated by 180 degree and red is on the right. So